There we go. Okay, so what was I saying? Your first homework's due tonight, 11:59 p.m. The second one has already appeared because they always appear on Tuesdays and are due on Tuesdays. So there's one day of kind of overlap. So make sure you're trying to stay on track of which one's actually due and which one's new. But the next one is 1-4 to 1-5. 1-4 we should get, well, definitely we'll be getting to today. And it's a shorter section, so we might even get through all of it, maybe not. But we'll get through 1-4 and 1-5 almost definitely by Thursday. So that's good. Now, I had skipped this example 3 for the sake of time last time, and I think, again, for the sake of time, I'm going to skip it again. It's just calculating the average rate of change between these two data sets. So if you want to look at the final completed answers on Blackboard to look at that one and get yourself some extra practice, go right ahead. But I'm going to skip it for sake of time so we can finish 1-3 and get to 1-4. Anyway, so reminder, we're talking about average rates of change. So remember, average rate of change is essentially the same thing as a slope because it is a slope. Remember, they're used in slightly different contexts. But so we can calculate the average rate of change with this f of b minus f of a all over b minus a. Again, reminder, it is the slope of a line, which is why we calculate it that way. So let's look at this last example because this is the last example for average rate of change, and then we're going to go to something slightly different. So we have, was there something else I wanted to say? Yes, quizzes. So I'll talk about the quiz on Thursday at the end. But the quiz you just took this past Thursday, I have them graded. They just haven't gotten into Blackboard yet. So those will be in by the end of the day. I will post the answers by the end of the day. If you're going to be in class on Thursday, you'll get it handed back to you. If you won't be in class on Thursday and want to see, you know, anything I might have written on it, just send me an email and I can scan it to you. It might not come immediately. You might need to give me a little while and I'll get around to it eventually. But send me an email if you won't be able to make it on Thursday and you'd like to see potential feedback on your quiz. Those of you who took it on Blackboard, I thought that Blackboard allowed you to view the feedback that I put on your quiz. One person is having a hard time, and the only person that I've had it as a guinea pig to try to figure it out. She said it wasn't working, nothing was pulling up for her. So let me know if there's no way for you to look at the feedback on your quiz. Google tells me that if you go into your Blackboard and you find the quiz grade and you like click on the grade, it should send you to feedback. But if that doesn't happen, again, and you want to kind of figure out where you lost points, just shoot me an email. All right. Anyway, I think that was the last thing I wanted to say. That was just generic stuff. So this example, a car travels away from home on a straight road. Its distance from home at time t, as shown in the figure below, is the car's average velocity. So remember, average velocity is the same thing as average rate of change, just in a very specific context. So is the average velocity greater during the first hour or the second hour? So first thing is, let me break this up into the first and second hour pieces. So average velocity, I'd really love to compare numbers here. Oh, wait, I don't have any y values. So I don't have any y values here, so I can't actually calculate the average velocity. So I need some other way to figure out which one's greater. Well, again, we need to remember that the average rate of change, while it is technically a number, it represents a slope. So let me look at the kind of line segments between these two things. So if I go from 0 to 1, to the best of my ability to draw the line between them, and then go from 1 to 2, and to the best of my ability to draw the line between them, which follows, that one follows the function pretty well, but the function is still not technically a straight line, so it doesn't follow perfectly. But anyway, so now I've got these two little line segments, and if I look at these two, this first one here is a lot steeper than the second one. Maybe I should be careful with the word a lot, but it definitely is steeper than the second one, right? First one starts out steep, excuse me, and then the second one is starting to kind of level out a little bit more, right? So the steeper the slope, well, the steeper the line, the larger the slope, right? Well, specifically for positive slopes. So since this line is steeper, we're going to be able to say that the average My words are breaking. That the average velocity is greater in the first hour. And let me write down why, just in case you're looking at this later and you don't remember. So the reason being is that so we can tell since the slope of the line between 0 and 1, 0 and 1 is greater. So maybe I'll even say line is steeper than that of the line between 1 and 2. So really the answer was just this piece here, but I wrote the second part just to remind us why that is the answer. So we didn't even need the actual numbers here. We didn't need to find the actual full calculations. We could just compare the slopes of the lines. Now, is that always going to work? Not necessarily. What if the slopes look really, really similar and you're not sure which one's actually greater? Then in that case, you would need the actual values. But in this case, there is kind of definitely a difference between the two. One is definitely more steeper than the other, so we can tell. So I know that we jumped back into average rate of change kind of quickly, and now we're moving past it very quickly. But are there any questions about average rate of change before we move on to a slightly different topic? I'll wait a couple seconds. It's going twice. Alrighty. So moving on. We say that the graph of a function is concave up if it bends upwards as we move from left to right, and the graph is concave down if it bends downwards as we move from left to right. And I'll draw some examples of that in a second if you're confused as to what that means. A straight line, so a linear function, is neither concave up or concave down. It has no concavity at all. A straight line is just a straight line. So we kind of have two choices here, concave up or concave down. So we've got whoop and whoop. I made those really big. So this piece would be concave up, and this would be concave down. Now, we've also got kind of two options for each of these options. I think I see new people. People who just popped in, can you see my screen? No one's saying no, so maybe I'm wrong about that thing, and my other class was just weird. Anyway, if you can't see my screen at all, ever, let me know. So even these concave up and concave down kind of have two separate choices in and of themselves. It's always going to have one piece that would be decreasing and another piece that would be increasing. Whereas this one has this side being increasing and this side being decreasing. Now, in terms of remembering which one's which, there's kind of a super easy way that I'll talk about in a second. But I also want to talk about kind of the reason behind the bend upwards, bends downwards. I think in terms of concave up, I think this side, it kind of makes sense that it's bending upwards because, you know, as you go, you're getting kind of steeper and steeper as you're increasing, right? So that side, I think it kind of makes sense that that's bending upwards. But this side, I think a lot of people have a slightly more difficult time understanding why that's considered bending upwards. So the way I like to explain it is, think about it as, pretend that this parabola that I have here for concave up is representing the position of a helicopter you're flying. Okay, so you're flying this helicopter, and this parabola is kind of tracing the position of your helicopter. On this first side here, you're kind of heading towards the ground, right? So, well, a terrible situation as it is, imagine you're crashing. You're heading towards the ground and you are trying to avoid crashing. You are trying to pull that helicopter back up into the air, right? So you're trying to have it, you know, go up. Now, helicopters can't immediately change direction, so it's not going to be some kind of sharp turn. You kind of have to slow down a little bit and kind of ease down before you can actually start heading back upwards, if that makes any sense. So that's why that side is also considered bending upwards, because as you go from left to right, it's trying to head more in the upwards direction, if that makes any sense. And again, there's an easier way to think about it. I'll explain in a second, but I always like to do this way anyway. And then for concave down, again, I think this right side kind of makes more sense, that it's curving downwards, because as you move from left to right, you're getting, you know, more and more negative, faster and faster. Maybe I should avoid the word negative, but you're going down faster and faster as you go from left to right. Whereas this side, again, imagine you're in a helicopter and you're heading upwards, but then you decide that you need to go back down. Well, you can't change direction immediately. You kind of have to slow down a little bit and then head back downwards. So that's kind of that bending downwards, is you've got to kind of, you're still increasing, but you're increasing by smaller intervals in each piece. Like, you know, it increased by a bunch here, but then it gets, you know, smaller and smaller little steps upwards. So that's why it's still considered bending downwards. Anyway, so that's my spiel about that. The easiest way to remember it is concave up like up, concave down like a frown, and then you just draw them. So concave up like a cup, concave down like a frown. And if you just draw the pieces, that's usually what people do, is they'll just draw the pieces on the side and refer back to them. So say we want to take this idea, and we're going to use the following figure. We're going to estimate the intervals on which it's increasing, decreasing, concave up, and concave down. So the increasing, decreasing piece we kind of already know how to do. So I'm going to breeze through that slightly, but of course, stop me if I'm going through it too fast, or if you have a question, as always. But you know, the increasing, decreasing is going to switch when it changes from heading up to heading down. So it's kind of going to switch at 2 and 6. So we have that first piece, and we're going to assume that this heads downwards and upwards forever. So that means that kind of first leftmost piece is going to be from -infinity to 2, and that's increasing. That piece in the middle from 2 to 6 is decreasing. And then from 6 to infinity is also increasing. As always, you could put brackets on the numbers, not the infinities, and still be 100% correct. So hopefully that's familiar. But now let's move to the new idea of this concave up and concave down. Now, this is unfortunately slightly harder to see, especially figuring out where it changes. And that's why it uses the word estimate, because we're going to do our very best. Now, in the future, in a few chapters from now, we will find a kind of calculus algebraic way to find exactly where it changes. But right now, we kind of got to work with what we got. So we're looking for concave up versus concave down. So the best way I can give you, that I can think of, to do this is, so remember, you kind of got two choices, concave up or concave down. So what I'm going to do first is I'm going to go and I'm going to locate all of the areas on this function that look like one of these two things. And I'm going to kind of draw some boxes around them. So I've got this part right here. You know, that looks like definitely a concave down piece. And I've got this part in here that definitely looks like a concave up piece. Okay, so that's what I mean by locate the areas on the graph that look like these pieces. So once you kind of locate all of the places where that happens, you can start writing your intervals. So I've got one box, I've got two boxes, which means I'm going to have two intervals. Since there's no other places on this graph that look like this, those are the only two, we're only going to have two intervals. Okay, so if you have kind of three spaces that kind of look like definitely concave up or definitely concave down, you'll have three intervals and so on and so forth. Hopefully that makes sense. Because essentially what's happening is the only time that it can change from concave up to concave down is if you see, you know, each of these two pieces showing up. So they kind of come in, nope, I shouldn't say that. They don't necessarily come in pairs because you can have three intervals. But if you don't have any more pieces that look like this, then again, it doesn't change anywhere else. To change from concave up to concave down, you must have one of these two things showing up. So essentially, what I'm trying to say by that is that from this first box downwards, like backwards to the left, that's going to be the exact same thing as whatever the heck this box here is classified as. And for this second box here, to the right of it, it's going to be classified as the same exact thing. And the only place that we're kind of ambiguous about is what's happening in this kind of middle section here. And it's got to change somewhere in that little ambiguous section. So in this kind of middle section, somewhere in there, it's got to change from concave up to concave down. So let's pick, the 4 looks like it's, in there somewhere. And that's a nice, actual integer. So let's go ahead and say it's probably about 4 where this changes. So now this first box, this first kind of box place that I have right here, that box, what's in that box is definitely concave down, right? So what's in that box is definitely concave down. And again, I've said that anything outside of the box until you get to a new box is going to be that same classification. So from negative infinity up to our choice of change of 4 is going to be concave down. Hopefully that makes sense. And then the second box here, this little piece right here is definitely concave up. So essentially all of the rest of it must be concave up. Oh, sorry, 4, not 2. So when you're looking for concave up, concave down, kind of locate the places where it's definitely one or the other, and then split it up between, those sections, and then whatever it is in that boxed section, it's going to be for the entire space up until a switching point. Hopefully that makes sense. I feel like my words that I'm choosing are very bad. Are there questions on that? Okay. Yeah, go ahead. Type it, say it, whatever floats your boat. Did you mean to raise your hand? If you're trying to say something, I can't hear you. David Morton. No? Okay. Yeah? So you'll have to unmute yourself if you want to talk. Or you can type in chat. Whatever works. So right next to the hand button, there's a chat button. So wait a couple more seconds to see if something pops in from you. Oh. No? Yes? Maybe? All right, if you have a question, feel free to still ask it, and I'll go back to it. But I'm gonna scroll down because I'm not seeing anything so far. Okay. From the following table, does f of t seem to be increasing or decreasing? Do you think the graph would be concave up or concave down? So here we don't have the actual graph. We just have a table. Now, technically, you could plot those values, but you're not exactly sure what's happening in between, so we're just going to stick with the table. Okay. Now, increasing or decreasing. So if you think about what that means, increasing or decreasing, you're either going up over time or going down over time, right? So, and it's in terms of the y values, right? Are the y values increasing or are the y values decreasing? In some, that's dangerously decreasing, or whatever fashion, So let's look at our y values here, our f of t. Those values are getting larger as we go from smaller x values to larger x values, right? So since those y values are increasing, the function is increasing. So since f of t is, maybe I'll say f of t values are increasing, f of t is increasing. increasing. Now concavity, just like with the graph, it's a bit harder and we need to do a little bit more work. So for concave up or concave down, the thing we want to look at is the slopes. Because again, we have to try to figure out this idea of, is it bending up or bending down? So let's look at the slopes here. So we're going to want to find our change in y's over, well, maybe I should use the variables of the question. Change in f of t's over change in t's. So let's do our little loops. So all of our t's are increasing by 5. So that's super nice. And then if I start looking at how the f of t's are changing, let's see, we increase by 0.5, and then we increase by 1, and then we increase by 2.1, and then by 3.8, and then by 9.6. And I obviously have these calculated out already. I'm not like magically figuring these out that fast in my brain. So those are our change in y's. Now, there's a little bit of a shortcut we could take here, but let me just do the full explanation anyway. So if I start writing out all of our slopes that we have here, so we'd have 0.5 over 5, we'd have 1 over 5, we'd have 2.1 over 5, so on and so forth, 3.8 over 5, 9.6 over 5, 13.1 over 5. Now, in this example, the quote-unquote shortcut we can take is because of the fact that all of the denominators, all of the change in x's are the same. So since all of the change in t's, again, maybe I should use the right variable, all of our change in t's are the same. They're all 5. So I don't even need to like punch this into a calculator to actually calculate the full decimals out fully. To compare them, I can kind of just look at the numerators, right? So if I look at these slope values are going to be increasing because those numerators are increasing, right? So since slopes are increasing, recording right? I did, okay. Slopes are increasing is going to mean this is concave up. That looks like an E. Concave up. So in a different color so that we know it's not quite for this problem. So slopes are increasing is going to mean concave up. But then of course that means that slopes decreasing is going to mean concave down. So when you're given a table, that's kind of what you need to look for concave up versus concave down, is you need to compare the slopes. Are the slopes increasing or are the slopes decreasing? Increasing would give you concave up, decreasing would give you concave down. Questions, concerns about that example? Okay. Questions, concerns about concavity, because now we're moving on to a different topic. Okay. Now concavity, just like with interpreting slopes, is going to disappear from our lives for a little bit after this section, and then come back once we've figured out what derivatives are, and we're going to talk about concavity again in that section. So this will kind of come back later, but it's introduced here. So anyway, moving on. The last bit of 1.3 is something called relative change. So imagine, you know, if I asked, would you notice a population change of 1,000 people? The answer would probably depend on where you live. If you live in Coyote, New Mexico, which only had 128 people in 2017, so let's imagine it's 2017. If 1,000 people decided to move there, they would definitely notice, because all of a sudden there's way more people than there used to be. But if you're up in New York City, where in 2017 there's 8.5 million people, probably no one's going to notice an extra 1,000 people sneaking in, you know? So it kind of depends on what you're talking about, kind of where you started versus where you end. So that's kind of this idea of relative change here, is it's telling us kind of the amount we're growing by or decreasing by, depending on how things are going. So when you have a quantity P changes from P naught to P sub 1, we define the relative change to be the following: change in P over P naught. Or you can think about this as the actual calculation, P sub 1 minus P naught over P naught. And I find that a lot of people will also say to themselves, end minus beginning over beginning, because they get bogged down in the little zeros and the little ones. Whatever floats your boat. Now note that relative change is a number without units, so that's super nice. We don't have to worry about units. And it's often expressed as a percent. Now, I gotta be careful with that phrasing. The thing we calculate is a decimal, and we usually then convert it to a percent. And especially in Wiley, you need to be a little careful of whether or not they're looking for the decimal versus the percent. If they're asking for the percent, it will usually, say the word percent before the blank, or there will be a percent sign after the blank to kind of tell you that they want the percent value, not the decimal value. But sometimes they do want the decimal value. Okay, so let's see an example of this. Let's go back to that idea of these population changes of 1,000 people. Okay, so 2 cities, so breaking it up. So let's look at this New Mexico City first. So they started with 128 people. And then if 1,000 people move in, and end up with 1,128 people. So they start with 128 and they end with 1,128. Sorry. The captions, I said 1,128 and it registered it as 1,100 complaining, and I just found that really funny. Anyway, so if I wanted to calculate the relative change here, we're going to have the ending value of 1,128 minus 128 all over 128, which is of course going to be 1,000 over 128. And this results in the decimal 7.8125. So that also means if I wanted to convert this to a decimal, if you forget how to do that, what you're going to do is you're going to take the decimal and you're going to move it 2 points to the right and then put a percent sign at the back. So this would be 781.25%. So that's why it's such an obnoxious change, is because their population just grew by 780%. So obviously that's going to be something that a lot of people notice. Whereas let's then move over to New York City. And now I've got to remember how many zeros million has. So, oh, and I wrote this wrong in my notes. Whoopsies. So they start at 8.5 million and they end at an extra 1,000. 8,501,000. So if we want to calculate the relative change here, so again, this is our starting point, this is our ending point. Oh no, do not do that. Okay, so sorry. Someone asked, well, why can't you cancel out this 128 and this 128? Oh, Lord Almighty. Because math. Sorry. I'm sounding very sassy. I'm not trying to be mean to you. This is just a really big thing in math that a lot of people try to do, and it's very much not a thing you can do. So say I put this in symbols, A minus B over B. We can't cancel those B's out because of this thing right here. So because of that negative, even if hello? Even if it was a positive, we still can't do it either, because if you have either subtraction or addition, combining those two things together in the numerator, you can't cancel in any way. The only way you're going to be able to cancel things is if things are multiplied together. So if this was A times B over B, go right ahead, go crazy, cancel those B's out. But once it becomes subtraction or addition, that is a huge no. You can't cancel when the numerator includes addition or subtraction. So that's why that can't happen. Tons of people try to do it. Don't do it. It's not possible. It's bad math. So that's why we can't do that. No, you're fine. I'm quite serious. So many people do it that it's probably good to just say why you can't do that. Okay, anyway, going back to this. So we're doing our end minus beginning over beginning. So our ending value was the 8,501,000 minus 8.5 million. Whoops, why is that a so many zeros? All over 8.5 million. Sorry, such a large number. So that's going to be 1,000 over 8.5 million. Ooh, here we go. And this is going to become 0.00011, let me round 8. Which as a percent, if I move that decimal 2 spots to the right, it's going to be 0.0118%. So New York City, if 1,000 people moved in 2017, would only see a population increase of barely 0.02%, which is why absolutely probably no one would notice unless it was their apartment complex or something. But anyway. So this idea is to kind of show how much a change affects the original value. So like both of these populations changed by 1,000, but one of the populations was changed in a much larger way than the other. So that's kind of what these are kind of showing us. So let's finish a few more examples of that. We ended at 4 or 5. We're doing all right. Okay, cool. So find the relative change in price for the following items if the price increased by 2. So we're going to increase, let me just write this down here, increase, because it kind of got separated. So we're going to increase by 2 in each piece of this example. So a gallon of gas costing $2.25. So it starts at $2.25. And so then we're going to increase that price by 2. So it's going to end up at $4.25. Sorry, I got too used to a pattern in there. $4.25. So the relative change there. So this is our ending value. So we do our p sub 1 minus p sub 0. So our ending value minus our beginning value all over the beginning value. So 2 over 2.25. This is 0.8 repeating. So for the sake of turning it into a percent, I will say 0.889. For these, unless Wiley specifies otherwise, I would say take 3 decimal points because then transferring it over to a decimal, to a percent. So take 3 decimal places to convert it over to the percent, because then you have 1 decimal place on the percent. So this would become 88.9%. So that means that the price of gas increased by 88.9%. Which kind of makes sense that it's so high because $2 was very close to the initial value anyway. So say instead we had a cell phone that costs $180 and we wanted to increase that price by $2. Well, $2 is of course not very close to 180, so it's probably not going to be very much. So we go from 180 to 182 because again we're increasing by 2 in each of these cases. So we have our p sub 1 minus p sub 0, so 182 minus 180. over our beginning value of 180. So 2 over 180 is 0.01 repeating. So let me take 0.011. I mean, we could take one more 1. I know I just said 3 decimal places, but whoops. You know what? No, let's take 3 decimal places like I said. It doesn't really matter. If nothing specifies the amount you need, then take however many you want. But that will be 1.11%. Well, no, I took the other one off. 1.1%. Sorry. Going back and forth. Does that make sense? Questions, concerns? Okay, so we've got these last two, and I'm going to sit in awkward silence for about 2 minutes while you try them. So one thing I'll say on example 11, it's asking about the amount of jeans sold, and we're going to take the original price to be the original sale amount as well. So I'm going to sit here awkwardly for about 2 minutes while I have you guys try those, and then we'll go over them, and then we'll move on to 1.4. 1.4 blank notes are already on Blackboard if you also want to be pulling them up while I'm sitting here awkwardly. But let me shut up for 2 minutes. Couple more seconds. Okay, hopefully that was enough time for you to at least complete one of them, if not both of them. So, a pair of jeans originally $75.99 was on sale for $52.99. Find the relative change. Ending value minus beginning value over beginning value will give you negative 23 over, whoa, looking at the wrong thing in the notes, 75.99, which should be negative 0.303, which would convert over to, I'm going to write it like this, 30.3% decrease. If you put negative 30.3%, that's fine, but usually when we change it over to a percent, we're then also putting it somewhat in context. So we'd say like the price decreased by 30.3%. And of course, once you put it into that context of decrease, you can essentially drop the negative because the word decreased is kind of taking its place, if you will. And then our pairs of jeans, so they sold for 25 pairs a week at first and then 45 pairs a week later. So our ending value was 45, beginning value was 25. So our relative change would have been 20 over 25, so 0.8, otherwise known as 80%. So we would say something like sales increased if we wanted context by 80%. And that's relative change. Questions, concerns? Before we move on to 1-4 for the last bit of clients. Sometimes these captions are not good. All right, so 1-4. So I gotta unshare this. I think I've actually got to pull up 1-4 and then share my screen again. There we go. Except it's not. Can I link? No. Okay, hold on. Gotta unshare again really quick. Wink. Wink. Come on. Do the thing. Thank you. Oh my lord. What are you doing? Don't do it. Sorry, my cat's starting to get into mischief. Don't. No. Okay. With that little break. 1-4. So again, these blank ones are on Blackboard if you want to try to grab them really quick. So applications to economics. So this is kind of where the business side of business calculus kind of starts coming in, because we do a lot of this cost, revenue, and profit stuff that a generic calculus course would not do. So some definitions first. So we have the cost function, which is usually going to be C of Q. Now, a lot of times, note, most of these are always going to be in terms of Q. Sometimes they're in terms of different variables, but most of the time when we're talking about cost, revenue, and profit, it's using Q for quantity. So this is going to give us the total cost to produce Q items. Then we're going to have the revenue function, which is going to be R of, ooh, I didn't write that one in. Ooh, terrible me. Revenue is going to be R of Q. I don't know why that's not in there. Which is the cost of associated with produce. I'm sorry. No, that's because I'm getting ahead of myself. This isn't the revenue function. I'm getting way ahead of myself. Good Lord Almighty. Sorry about that. So the cost function gives the total cost to produce Q items. There are two types of costs, and that's what goes in these blanks. We have the fixed costs. The fixed costs are the costs associated with producing no units. So it's essentially, even if you don't make anything, you are still probably going to have to pay, you know, the rent for the building, the electric bill, the cost for materials, all the stuff that you need to pay for before you even start making things. And then there's the marginal, which is also sometimes called the variable costs, or costa, which is the cost of producing the next item. So essentially, you've made 5 items. How much more is it going to cost you to make the 6th one? Okay. Or you can also think about it as how much does it cost you to produce each one? So say like you crochet things and it costs you $2 in materials to make each one. Then your variable cost would be 2, because for each extra thing you add on, your costs are increasing by 2. If your cost is linear, which is the only type of function we have at this point in time, we're going to have some popping up in a bit. The next section, 1.5, is our next section of the next type of function we're going to talk about. But anyway, if it's linear, then it's kind of nice because the marginal cost, it doesn't look like an A. The marginal cost is just the slope. And then the fixed cost those are usually fixed costs, but anyway, is the y-intercept. Okay, so when it's linear, those kind of just fall out. Now, the y-intercept one is true always. So even for other functions, other types of functions that aren't straight lines, the fixed cost is still going to be the y-intercept. So maybe I'll put always. This one is kind of true always. It's a bit different context, but again, we'll come back to that idea once we have the other types of functions. I'll kind of explain where the marginal cost shows up there. But there is still marginal cost and fixed costs for absolutely any cost function, whether it's linear or not. But in terms of linear functions, it's kind of super easy to pull out because especially if you have the equation y equals mx plus b form, then you just pull out the m and pull out the b. So let's say we have a radio factory that's going to create radios for $7 per radio. So that phrasing means it's costing them $7 to make the radio. So they create the radios for $7 per radio. Labor and raw materials costs are $24,000. Find and sketch the cost equation for the company. Label the marginal and fixed costs on the graph. So assume it's linear. Technically, I probably should have written that in there. We only have linear functions to deal with right now, so that's what we were going to do anyway, but usually it should actually specify that you can assume it's linear. So assuming it's linear, we want to find this equation. So we need some C of Q, and since it's linear, it's going to be some kind of MQ plus B. So yes, I'm using Q's instead of X's because, again, cost functions, that's usually what we use. So again, so this one's going to be my marginal. This one's going to be my fixed. So my fixed is what I pay even before I start making things. So that's, in this case, the labor and raw materials. The people who sell me that stuff, you know, the people who are working for me don't care if I make nothing. They still want to be paid if they're there. And the people who sell me the raw materials don't care if I make anything. They want to get paid. So even if I don't make anything, I'm still having to pay $24,000 to someone. So that's going to be my fixed cost. And then since the radios are costing me $7 per radio I make, that's the marginal. So our equation here is 7Q plus 24,000. So say I wanted to sketch this. And again, sketching for me is usually, I'm going to make this somewhat nice. So I'm going to kind of break it up kind of nicely. Let's do 100, 200, 300. So I'm taking the sketch to a bit more of a decent level than I usually would do. But let's do it. And let's go up by thousands here. So if I wanted to sketch this, so the 24,000 is, of course, my y-intercept. So I'm going to draw that where it crosses the y-axis. So about 24,000 is going to be about right here. And let me go ahead. I know I said sketch, but I also just said that I'm going to make this a little better than usual. Let me go ahead and find some other points at this 100, 200, 300, and 400. And I'm going to do that easily using the slope. So I'm going to use the idea that if Q increases, say increases by, oh my goodness, by 1, then C of Q increases by 7. Yes. Yes, there should be 10,000s, not 1,000s. Thank you. I'm dumb. Thank you. So if you think about it, oh, that throws everything off. Oh, it'll be all right. I'll figure it out on the fly. So the slope would tell me if Q increases by 1, C of Q increases by 7. But now if I'm increasing by 100, that's going to tell me C of Q is increasing by 700, right? I'm just multiplying the 7 by 100 to get 700. So yeah, now that my things were off, that's going to make this less nice. But you know what? It's going to be fine. So when I go over to 100, I'm going to increase my cost by 700, which is going to make it 24,000 700. So it's going to be like just above this one. So 24,700. If I increase by 200, if I increase to the next 100, I'm going to increase that cost another 700. So add 700 to that, we get 25,400. That's going to be just above. Again, because I screwed up those Y values, this no longer looks nice, but oh well. And actually, because I screwed that up so bad, we're just going to stop there and get those two. So this is going to be a pretty, you know, not very steep line we got going on here. But I've got 3 points on there. That's good enough. Got to fix that in my notes. But that would be our generic sketch. So since 24,000 is such a large number compared to, you know, the slope of 7, we know we have a pretty not very steep line. The slope of 7 in this case is not doing too much. So hopefully that made sense. Oh, and we were asked to label the marginal and fixed costs. So let me do that in a different color so that it kind of pops. So this right here was our fixed. And then our marginal is going to kind of pop in this way, you know, kind of bringing in our little slope triangles here. So this increased by 100, this increases by 700. So this piece here is kind of going to represent our marginal. And I'll say slope to remind us that that's actually what we're looking at here. Is the slope here is giving us our marginal cost. Okay. So, any questions on that? I assume they would have popped up already, but give it a couple more seconds. It's cool. Next example, sketch. Now we're really going to sketch. Sketch a graph that would satisfy the designated situation. Fixed costs are large, but marginal cost is small. Well, that's kind of what we were just looking at, is we had a much larger fixed cost than marginal cost. So that gave us something that was pretty, you know, high up on the y-axis, which would be the large fixed. But then the small marginal cost means we're going to have a very small slope, and the smaller the slope, the less steep the line, you know, so we're going to have I'm going to make that even less steep. I'm going to make it obnoxious. That's a very not steep line. There we go. And maybe just to get the point across, small slope, which was the marginal. So if I just wanted to sketch the idea of large fixed costs, small marginal costs, I just want a large y-intercept and a small, very not steep slope. Or as opposed to the next one where it says no fixed cost, but marginal cost is high. So no fixed cost means that my y-intercept is 0. So technically I still have a fixed cost, it's just that the fixed cost is 0. So it does make sense to say no fixed cost because this is in terms of money. And when you say it has no cost, it's 0. Technically, if you want to get technical, the fixed cost is 0. So there is technically a fixed cost. Anyway, semantics. Hopefully it makes sense that no fixed cost would imply that it's 0. But then the high marginal cost means that my slope is large, which means I have a pretty steep line. So we have, you know, a really steep slope, which was, again, what are you eating? Stop it. Hurry. Go take a nap or something, Maz. Sorry, a cat. Okay. So, hopefully that makes sense. 10 more minutes. Let's try to finish out that, and that'll be good. So, a few more definitions. Now we get to revenue. So I was way ahead of myself before. So the revenue function. Revenue. Which is R of Q, gives the total revenue received by a firm from selling a quantity Q of some goods. So I know I just used the word revenue in the definition of the revenue function. this is essentially the amount of money you make from selling things. So a lot of times we'll also say that revenue is price times quantity times, or just abbreviated to P times Q. This is really important. We're going to have to pull this out a lot. So you might want to write that down if you're just taking kind of simple notes. And then we have the profit function. Now this is denoted by pi of Q. Why do they use pi? I actually don't really know, but it's used pi of Q instead of a P. So probably for probability's sake, because P is used in probability a lot. Anyway, so pi of Q, and this is going to be calculated by taking revenue minus cost. So you're also going to want to really remember this piece here, revenue minus cost. A lot of people get it flip-flopped, but also you can kind of talk yourself through it. It kind of makes logical sense that that's the order it has to go in. So if you think about it, profit is the amount of money that you get to, like, actually take home to your mom and be like, Mom, look, I made this much money today. And if you think about that, how you get that, it's how much money you had in general, how much money you got from selling all of your items, the revenue. But then you have to pay, your workers and the bills and whatever. And anything that's left over once you pay all that stuff is stuff that you get to keep. So it kind of makes sense, and you can kind of talk yourself through it if you forget the order. So it's the total amount of money you have minus the stuff you have to pay to people. So revenue minus cost. Anyway. And then we have the break-even point. And this is where the profit is going to be 0. And so that's essentially saying that they break even. They finally have sold enough things to be at 0 profit. They're not in the red anymore. But also, if you think about it, so if profit equals revenue minus cost, and we're talking about when profit equals 0, then we're also talking about when revenue minus cost equals 0. Which if you swing cost over to the other side by adding it, you get that revenue equals cost. So we're kind of going to jump between those two kind of options. We're either going to be able to set profit equal to 0 or set revenue equal to cost, kind of whichever one makes it easier for you to calculate. All right. So I'm going to scroll down just a little bit. I'm going to try to leave most of these. Well, we'll see the instructions and then I'll move down some more. And hopefully everyone will have gotten the words by then. So let's try to, we should be able to get through this example. This will be the last thing we do. So consider that radio factory again. Same radio factory we were just working with. Now so they, oh my lord, say they sell each radio for $15. So first I want to find the revenue and profit functions, then the break-even point, and then we're going to sketch some graphs. So does everyone have all of those definitions? If anyone needs me to hold on, I will talk about the quiz on Thursday at the very, very end. Yes, I will. But we're going to finish this first. So first thing, find revenue and profit functions. So again, revenue is price times quantity. Again, I told you you're going to want to remember that really well. So here, the price that they're selling them for is $15. So here, our revenue function, and I'll put actually our this time to be formal. It's going to be 50. It's going to be 50. That was weird. Did someone have a question? Okay. So 15Q there. So now we want to find the profit function. So the profit function is going to be our revenue minus our cost. So our revenue function we just found was 15Q. And if we go back to the previous example, our cost function was 7Q plus 24,000. You need to be very careful when doing profit. Always put the cost function in parentheses because you're most of the time going to need to distribute this negative. Because if I want to finish simplifying this out, I do have to distribute this negative. I get 15Q minus 7Q minus 24,000, which results in 8Q minus 24,000. And let me just bring down the pi of Q just for formality's sake. We'll hold on a second if there are questions on that before I go on to part 2. All right. Why do we use pi? I honestly don't know. I think it's because this means something else in probability, like something very meaningful in probability. It means the probability of X. So I think it's probably to avoid that kind of overlap between probability and profit. I don't really know why they would ever be used together, but no, it doesn't mean. So here, pi is just being used as like a, this isn't saying 3.14 times Q or anything like that. It's just used as a symbol. If it makes you feel better and you want to use P of Q, mad at you. Like, I'll understand what you mean if that makes you feel better. But technically, the formal one they use is just pi. I don't really know why. So the break-even point, again, is defined to be when profit equals 0. We have our profit function. We're going to set it equal to 0. I would personally add 24,000 over to the other side. Ran out of space. Are you attacking my feet? Stop being a brat. Oh my god. You get Q equals 3,000. And I think I'm actually going to leave 3 and 4 for later because I want to talk about one last thing, and we'll do that as like a intro thing next time. So we just found that Q equals 3,000. That doesn't look like a 3. And of course, this is now breaking at the very end. 3. Okay. The break-even point is a point. And so usually a point is, you know, 2 different values, an x comma y, right? So here, whenever we find the break-even point algebraically, there is a second part that we're going to need to find. So we just found what we call, let me use another color. Oh my word, go away. Oh, why is this design? There we go. Break-even quantity. Because it's the Q value, it's the quantity. So we just found the break-even quantity. But we also have need, and I'll go over this again on Thursday, break-even price. And the way you're going to find that is you're going to take Q, and you're going to plug it in to either cost or revenue. Not profit, because profit would be 0, but that's not actually what we care about. I'm going to stop here, and again, I'm going to come back and reiterate this again on Thursday and find out what it is. It's 45,000 if you care. You just plug 3,000 into either of those two functions, you get the same thing. So we'll finish off that example on Thursday. And I'll kind of go through it again, this second part, to kind of remind ourselves everything, because I slightly rushed through it a little bit. The quiz on Thursday. Well, before I talk about that, any last minute questions about this? Okay. Quiz on Thursday. I will type in the chat the things you should be looking into. So quiz on Thursday. This is going to mainly focus on 1.2 and 1.3 still. So I know we just started 1.4, but that'll be kind of next week. So you're going to want to look at linear versus nonlinear, kind of like what we did at the warm-up. Is this data linear? Is it not linear? finding linear equations. So if it is linear, can you find the y equals mx plus b? And then average rates of change. Ask you to find the average rate of change between two values. Can you do so? Those three topics are now in the chat, so you can go back and look at them later if you want. That's what will be on your quiz on Thursday. Again, your grades for this past quiz will be up on Blackboard by the end of the day. If you take it online and you can't find the feedback, let me know, and I will let you know what you lost points on. If you won't be in class on Thursday and you want to see your quiz, email me and I can scan it to you. Stop being a brat. If someone wants to come get my cat, no, I'm kidding, you can't have her. Besides that, I think that's about it. Have a good day. You can, of course, leave if you have questions. Feel free to stick around. Can we meet your cat? Hey, Maz. But apparently not. She's not very happy. That's Mazu. She's very hungry, and that's why she's being a brat. You'll get dinner in a second. Come. You're welcome. Again, feel free to leave. We're done. Have a good day. I should stop the recording. And now there's a recording of my cat. Okay.